Good morning, everybody. How's it going? How's Git so far? Some energy? Come on, yeah, let's go. That's what I like to hear. Okay, so we will talk about optimization of Niagaras. Basically, all the stuff that I put in Frostpunk 2. And yeah, wait, is it? Okay, so some facts about me. I'm working in industry for 5 years right now. Worked on several AAA projects like For Solis, Frostpunk 2, of course, Path of Calidra, stuff like that. I finished Peyote TK, but to be honest, academy, like I didn't. Mostly it was about connecting. I didn't learn much stuff there, but whatever. My main passion is games, of course, but I'm making music as well. I'm really loud. I'm really eccentric. So yeah, let's get into it. What's agenda? I won't talk about like the basic stuff with Niagaras. We will learn something about the structure of the whole emitters and stuff like that. We will talk about materials. We will talk about Niagara Effect Types, things that aren't put it in documentation for some reason. So I had to just do it by myself. So let's go. Basic phrases about the optimization is, of course, performance. What is a performance? Performance, it is time that we are, at what time we are rendering the whole, like the frame itself. Culling is another basic phrase. In computer graphics, it's basically, there's notes as well. Can I have these notes here? No, you see everything here. Okay. So yeah, you do you, I will do me. Basically, there's different versions of culling, as you can see in my notes there. There's a backface culling. No, we can do it. Okay, I will do it from your memory. There's a frustum culling, or maybe, you know what? Because it will be much easier for me. Yeah, exactly. Okay, so we have a backface culling. It is a technique that involves removing the faces that are not visible in the camera view. Like the normal of the vertices itself is just facing another direction, so we don't have to render it. We have a view frustum culling, and so when camera doesn't see like some object, we just don't render it. We have occlusion culling. In this method, objects that are completely occluded are just not rendered. So we basically want to only render the things that we are like see in a camera stuff. So let's talk about the Niagara emitter by itself. So as you can see, okay, like the colors are not great, but whatever. We have a system grabs. This thing, that's blue, and these modules execute first and handle behaviors and variables across the whole system. That's really important that those variables are for a whole system are like mainly the same. We can set those variables inside the blueprints. We don't have to like put it inside Niagara itself. We can drive it from another level of it. So we have emitter grabs, and as you can see, there's the whole emitter A thing. We have emitters path, and these things are managed. It always works on CPU, and it's really important to know because some features like I don't know, like sampling RVT or something like that we can't do it on CPU because it's on GPU like mostly. We have an emitter spawn and emitter update. Emitter spawn and emitter update is basically things that are, emitter spawn, so it ticks only once at the spawn of the system. It's really important to know that we can't update those variables across the lifetime of the whole emitter because it only takes once. So it's the best way to put some variables there that won't change across the system. We have a particle groups, and these modules execute for each unique particle within an emitter. So if we're spawning 100 particles, for example, we can manage them, change them over time or something like that. And the last thing is a render group. And these modules handles the variables that we gave across the whole emitter, and we render those variables in some reason. We have a sprite renderer, mesh renderer, decal renderer, and a component renderer. And I don't really recommend using the last one because it's still experimental feature. But feel free to explore this stuff. You can spawn multiple blueprints, for example, from a emitter itself. Oh, okay. So, emitter properties. When we're making the new emitter, we can set it in a local space. We can set determinism there, interpolate spawning. And if we put this emitter in GPU space, we have to put fixed bounds as well. What is a fixed bound, you will ask? I will answer, of course. It is, you can, there's the box that occludes the whole emitter. And if camera doesn't see this box, this fixed bounds, then it just don't render. And we can set those for each different emitter by itself. It's really important to keep it as tight as possible, so it will be occluded great. But yeah, we have a lot of different things that we can set it here. Important thing to know is we don't always need all variables. So, for example, we don't always need unique IDs for a particle itself because, I mostly use it only when I'm emitting ribbons or stuff like that, because the less variables are better, basically. So, preparing material for Niagaras. If you making a master material for your game, it's really important to put this inside the functions, and it looks good in material. It's really clean, to be honest, but the most important stuff is that you're not individual. There's another VFX artists that are working at your game as well. So it's really important to keep it simple, keep it really visible. So if anyone else go inside your material, he will just quickly knew what's what, and you can optimize this thing even more. It's really important to have as less master material in your project as possible. In Frostpunk 2, we have 3 master materials for VFXs for a whole game. And we mostly just put the material instances there because we used a lot of, as you can see, material functions, stuff like that. We could iterate it as much as we want to, but there is that hidden feature inside the Niagara is that we can put every dynamic parameter and drive it through the emitter at the emitter spawn. So it is driven from CPU. That's important because it's not optimal as you would want, but you can reduce you can you can reduce draw costs in that way. So if you're making the materials inside the Unreal itself, you have platform stats and stats. For some reason, I don't know why, to be honest, but those are HLSL, instruction counts, not GPU cycles estimate. And what we want to, basically when we're optimizing materials, we want to go through the GPU cycles. We don't really care about that instruction counts because it's, well, it doesn't give you the proper cycle values. So you have to go to some, if I remember correctly, there's a Tom Jones site, something like that, and it's just disassemble your HLSL code inside the Radeon cycles, and you can check there how does it cost. And one more important thing, when you're going inside the material editor, you have this thing, automatically set usage in editor. I recommend all of you to disable it because every flag that you have inside your material compiler costs at the shader complexity when you're shipping the game. So it's really important to only have flag costs, those flags, for a material that you really use this material. So let's talk about shader complexity. Shader complexity, basically, in FireFixes, it is mostly like about the translucent sprites. So if you want to make some really fancy explosion or stuff like that, you really need to put a lot of sprites, translucent, at top of each other, and we have to overdraw them. So what we can do to reduce this thing, we can use cutouts, for example. As you can see, it is driven from a sub-image index. It is a variable that basically drives the animation of a flipbook. If we have a 64-frame flipbook, it is driven through this sub-image index binding, and you can find it in a render at the very last stack of render stuff. And yeah, it is a really, really quick win, and it works perfectly. Really recommend it. But there is another thing, because when you're thinking about the FireFixes in general, you have to think about the spawning of a particle itself. You have to think about the shader complexity of cost of the material itself, and how do we check all this stuff. So we have a thing that's called Niagara Debugger. In performance, you can put it FX outliner. As you can see, there's things there. And how are we optimizing stuff? It is a 30-minute talk, so that's why I'm speeding so much, sorry. But when you're thinking about the FireFixes, let's talk about Chimneys, for example. We have a lot of like districts in our game in Frostpunk, and there's a lot of the same behavior, just iteration of it, like chimneys, people on the streets, or something like that. We don't have to spawn each Niagara for each chimney. We just can optimize it in a different way. We use the thing we call emission points, and we just get we get the whole. Sorry. I'm back. Okay. So we're basically having an array of positions, and we put all those positions inside one Niagara. And instead of spawning 10 different Niagara systems, we're spawning only one, and we iterate it. And we reduced the memory usage like 5 times with this simple thing. So if you don't really need to spawn those Niagara systems, you just don't have to. Like, why bother? Okay, they are making the point that. Okay, so in ScratchPads are basically the modules that you're putting inside the Niagaras, and you can write your own code inside there, and you can iterate everything there. Like inside the render bindings, you can put different position, you can put different colors, you can put different velocity values inside, and it all can be the same emitter. As you can see here on this GIF, right now we are seeing 3 emitters, and we can do the same stuff. That's basically everything is the same, but within the one emitter. Just iterate the variables that we given to that we give to the render stack. So generally, if we're talking about the optimization of Niagaras, less is better, right? So as you can see here, we have the 3 emitters, big thing, circle, red circle. Okay, like, but the behavior of an emitter itself, like, doesn't matter at all. We can do it, everything inside the one emitter with the 3 different renderers. And of course, because when we are spawning emitter, we are using CPU, right? We don't really want to use CPU at all. The more GPU usage is the better, basically, because we have to leave the CPU for AI stuff, like some things that just have to use CPU. Niagara doesn't have to. So, to properly redistribute budget of your FireFX, you should, and of course, you have to like put visibility culling inside there. There is the thing that's called Niagara Effect Types, and you can batch the whole like systems within your project inside there and put some values. Like, I don't know, if we don't want to render smoke or something like that after the distance of 10K or something like that, we can batch them and optimize this stuff as well. It should almost always be on low, of course. It really depends on the system that we did, because we have something like muzzle flashes or something like that. If we have a system that's basically burst spawn, well, we can just check it at the spawn, and we don't have to update this fast-run callings and stuff like that almost never. So, scalability. As you can see, this is the screen from a Niagara Effect Type itself, from this asset. We can put there 4 different callings. We have a distance calling that's like basically after some distance we don't render this thing. Budget scaling is the thing that your TechArt lead will set up probably. And if we like cross some budget, then we can't like spawn this Niagara system. Visibility culling, so if camera don't see this thing, then we don't want to render it. Instance culling is so if we're making footsteps, for example, we have a spawn that's procedurally generated. We don't want to have like 30 or 40 instances of the same system. So if we cross the given quantity of the systems, then we just don't spawn it. Really, really useful if we're making some procedural stuff. Yeah, and tips and tricks. So, if we're making some cinematic Niagaras or stuff like that, it's really, really painful to like micromanage this lifetime choices. We can just bind the level sequencer of a Niagara. We can bind the age of a sequencer to Niagara, so it's basically driven the system age variable that's put it across the whole system. So it is really, really useful. If we're making the new modules, for example, and it's given for the whole project, like, I don't know, across the 10 or 12 systems. In Frostpunk, we had a Niagara module for generally like the people inside the city, and we shared the same modules across the different systems. And there's the thing that's kind of hidden, but it is a versioning. It's really helpful if you're making the really big project. And yep. And when building your Niagara systems, you can get the variables that you need from Emitter itself. Basically, inside of a ScratchPad itself, it's just better visibility of the given system. And yeah, really useful. And same thing is with net. So net is that Niagara Effect type that I told you. Like, you can set the distance scaling, for example, there for a 10K, and you can get this value inside the Niagara itself. But it is a normalized variable, so it won't be like 10K. It will be just from 0 to 1. I put it into the spawn range, for example. So if we're almost at the distance from calling, spawn just reduces to 0, and it's a really nice, like, smooth interpolation of turning on and off the effect itself. And well, inside the materials, we have a lot of different nodes that basically you can use them inside the materials, inside the Niagaras as well, but you can modify them, as you can see. There's a dynamic parameter, for example. I used it for mapping the vertices of the mesh. For example, you don't have to put the float values there. You can map it to anything you want, basically. Like, it is really, really useful. I recommend you to download the matrix demo of Unreal 5. There's a really great shader for that uses the mapping vertices to the dynamic parameter inside the Niagara there. And it's, of course, free on the Epic. So, and you don't need that much material instances when using Niagaras. You can bind it inside the render parameters at the very bottom of the stack. What's important here is that those variables are only driven through CPU, and it kind of makes the new material instance, so it won't be that optimized. It is another draw call, of course, and those are really CPU heavy, but you can drive the, for example, fluid simulation with this thing. It doesn't have to be vector or float variable. Okay, I get it. It can be even a texture or a curve. You can put any variable that you want. Thank you so much. Any questions? I can hear you.
How do you pass the information from the, let's say, camera itself? Because how is it
You mean when I have the multiple cameras?
How do you know? How do you know that camera sees the bounce, certain bounce of the let's say Niagara emitter?
You can set the camera like the main camera itself. Like it's always. Oh come on! Like maybe another way. There's always the main camera inside the Unreal itself. Like because like Unreal is not the engine to build anything but FPSs. Like it is driven for FPS, and it's really painful to do strategy game or anything else inside the Unreal itself. So you have to go inside the code and like point it to the Niagara itself.
But do you use some kind of line trace or something from camera?
Yeah, it is a line trace, but it's driven through the GPU, so it's not performance heavy at all. It's almost free.
Okay, and the last question, let's say, if you have a, do you use the result of the line trace, like yes or true, to then drive the size or the complexity of the Niagara effect itself? Do you pass the information like yes or no, like the Boolean, to the then to the Niagara to drive?
I don't understand the question. Sorry. Like, do I?
How does it work? If you want to, let's say,
Okay. There's the update frequency. Basically, it's 1 tick per second mostly, but I recommend to even decrease it to the 5 seconds, so it will be 1 tick per 5 seconds, for example. And yeah, it is like a Boolean because it have to be the most optimized like information as you can like get. So basically, it is a Boolean. If camera sees it, then it's okay. We are spawning it. There's a lot of different, of course, calling versions and stuff like that. So it is kind of complicated, and there's not much documentation about it.
let's leave it. Can I have just one single question? What's the main difference between built-in scalability options that ones that are built in game, in the engine itself, compared to your custom, let's say, logic? You have told us about
What's the difference there?
the main difference.
You have more flexibility when spawning itself, like and like mapping distance to the spawning or mapping phosphorus calling to the material itself really helps with the visibility of the stuff. You know what? I have this presentation on ArtStation, of course. Like, feel free to go there. I know that I was speeding today, so but you can just go to my ArtStation and see it and just copy it. So thank you once again.